For this simulation video, we are going to do the laboratory activity number 15, which is the implementation of the IND sampling rate converter. So first of all, what is multi-rate? Multi-rate means multiple sampling rate. A multi-rate digital signal processing system uses multiple sampling rates within the system. Whenever a signal at one rate has to be used by a system that expects a different rate, the rate has to be increased or decreased. Let's say, for example, the input signal will come from a telephony which is capable of 8 kHz, and the receiver or the output would be an ACD, which requires a 44 point something kilohertz. That means the sampling rate needs to be increased, and some processing is required to do so. Therefore, multi-rate digital signal processing refers to the art or science of changing sampling rates. Resampling basically means combining interpolation and decimation to change the sampling rate by a rational factor. Resampling is done to interface two systems with different sampling rates. Now let's go in running the program in MATLAB software. So for the code, first of all, we're going to get the required inputs. First is for the L variable, we're going to store the upsampling factor value. For the DU variable, we are going to get the downsampling value. For the N variable, we are going to get the length of the input signal. For F1, we are going to get the value of the frequency of the first sinusoidal. For the F2, we are going to get the frequency of the second sinusoidal. Next is for the X variable, we're going to store there the total of the two sinusoidal, or basically the frequency. For Y variable, we're going to get the resampling of with the parameters the frequency, the upsampling rate, and the downsampling rate. Now we're going to plot it. The graph would have a title of input sequence. For the first graph, it is going to have an X label of time, and for its y-axis, the label will be amplitude. The same goes for the second graph. The only difference is that for the second graph, it would have the title output sequence. So running the program, first is it would ask us to enter the upsampling factor. Now we are going to enter the given upsampling factor, which is 3. Next is we're going to input the downsampling factor, which is 2. We're going to have a 40 for the length of the input signal. Next is for the first sinusoidal, for the frequency of the first sinusoidal, we're going to have 0.01. And we're going to have 0.03 for the second sinusoidal. And this is the output. The first graph is the input sequence, and the second one is the output sequence. Now let's try another one. This time we're going to have 6 as the upsampling factor, 3 as the downsampling factor, 50 for the length of the input signal, 0.02 for the frequency of the first sinusoidal, and 0.05 for the frequency of the second sinusoidal. And this is the output for the second simulation. Now going back to discuss the output, we can see that since for the both simulation, we have a higher value of upsampling factor for the both simulation, and as we can see, it reflects on the output, because for the first output, we can clearly see that comparing the input and output sequence, we can see that the length of the output has increased, as well as the sampling rate. And we can see it by looking at how many lines or how many plots there are in the graph. And the same goes for the second simulation, or the output of the second simulation. So for our analysis, in doing the laboratory activity, we have observed that the multirate is simply the combination of upsampling and downsampling, or in other words, it is basically increasing or decreasing the sampling rate. The behavior of the input signal does not change from the upsampling or downsampling. It simply changes the sampling rate of whatever has the higher value. For instance, if the upsampling rate, just like in the simulation, is higher than the downsampling value, the output signal will still have the same behavior, but it will have more samples than the input signal, and the length will increase since the sampling rate has increased. On the other hand, if the downsampling has a higher value than the upsampling, then the opposite will happen. For our conclusion, by resampling a given sampling frequency, it is being interpolated and decimated with respect to a rational factor in order to change the sampling rate. It is used to interface two systems that have different sampling rates. Thus, if the ratio of the two system rates is an integer, resampling must be used to change its rate. The resampling factor is computed by dividing the interpolation factor with the decimation factor, or simply the upsampling with the downsampling factor. Since it is a combination of interpolation and decimation, the filtering process is also executed whenever resampling is used. To further discuss our analysis, we have here a different situation or different instances. For the first instance, we have the default input, which was discussed earlier in the output. The second instance is the equals upsampling and downsampling. In the simulation, we have an equal upsampling and downsampling factor. And because of that, since it was said that is basically the interpolation divided by the decimation, and since both have the same value, we can see in the input sequence and the output sequence that there has been no change. For the third instance, we have reverse upsampling and downsampling from the default input, meaning this time the downsampling is higher than the upsampling. And as we can see, Comparing the input and the output sequence, we can clearly see that the length of the output sequence is shorter, and we can see that the lines or the plots or the sampling rate is also less. Last is a double default input, or doubling the given input. We have upsampling factor value of 6 and downsampling factor value of 4. And just like the first instance, you can clearly see that the output sequence have more sampling rate and the length is longer. And that is it for the simulation of our laboratory activity number 15.